Okay, hello everyone. Welcome to this, the third edition of the WebAssembly workshop, Betraying Popple, by appearing now in ICFP Splash. So thank you for all coming. Our first speaker is going to be Andreas Rossberg, who almost needs no introduction at this point, and he is going to be giving us a talk on SpecTec as well as a practical demo. So please take it away.
Yeah, okay, thank you. First, what's new in WebAssembly land? So some of you might not have heard yet, but as of a month ago, WASM 3 is released. So, pretty substantial release, much bigger than the 2.0 release we had before. So with new features that have been in the making for, I think, almost since the beginning, actually. So for 8 years, like things like garbage collection. We now have low-level support for garbage collection. We have support for exception handling. And finally, for the first time on the web, we managed to get it in tail calls. Right, and there are other things like 64-bit address space, so you can now build much bigger applications. There's the gap we filled in the design with multiple memories, and there are a whole bunch of other goodies. But this talk's not going to be about that. This talk is going to be about specifications. Oh yeah, but I should mention, all that has been shipping in browsers already some of that years ago. So it's all there right now in all the engines and browsers, and it's ready to be used. So you can target it right now as we speak. Okay, but that's not what the talk is about. The talk is about specification, the specification of WebAssembly. So one of the features of WebAssembly that sets it apart from other mainstream industrial programming language technologies is that it's fully formalized, right? And I always have to explain what I mean by fully here. By fully, I really mean end-to-end. So from the first byte of the binary format to the last bit of what happens at runtime. And what we're using to do that is really like a textbook formalism, like you would see in every second paper on a conference like this. So we really try to do not anything fancy or new but to show that these techniques are sufficient for handling WebAssembly. And the other interesting part here is that this formalization is not just something we did on the side, it's a central part of the language standard. It's a normative part of the language standard. And in fact, the whole specification is centered around the formal semantics. So that's, again, pretty different from any other major language technology. So here's a peek of what it looks like. This is a page from the spec that shows the execution semantics of a couple of instructions. I won't go through all of that, but there are a couple of things to see here. So one is we have the formalism, which is small step reduction rules. So this would be, for example, for the BR-if instruction, which conditional branch essentially. But we also have, so that's all like should be familiar to this kind of audience. But of course, we have a much larger audience for a document like that. And most of the compiler writers, for example, they are not that familiar with that. They want to read some prose. So we also have the prose specification, which is supposed to express the same thing. So there are these two formulations. One is the formalism, which is sort of declarative. And then there is the prose, which is more algorithmic. It's defined in terms of like pushing and popping values to some stack machine. It's obviously a bit more hand-wavy. And they're supposed to be equivalent. And in case they are not, then that would be a spec bug, right? So they're both normative in that sense. Similarly for validation, which is our term for type checking, or what the JVM would call bytecode verification, that's just typing rules. And again, they're pretty nice inference rules like you would expect from a decent paper, but also equivalent prose that kind of spells out the conditions as text, as stylized English text. But it's not just that we have a formalization, we also have a mechanization. So meaning that we have fully machine verified soundness proofs for all these for the semantics. And again, this is not just for an idealized subset, it's for the full language as specified, right? And this is thanks to people like Konrad and others on the WASM cert team who did all the work for that. So there are actually two mechanizations. One is in Cork and one is in Isabelle. And currently that is handling WASM2, but there's ongoing work to extend it to WASM3. So another kind of unique feature about WebAssembly then is I think it's the only low-level language that has a completely specified semantics and absolutely zero undefined behavior, right? Thanks to all that, among other things. So, and that allowed us to put like these nice theorems into the actual language standard that we have soundness, like the typical syntactic soundness theorem about progress and preservation. So this is an actual part of the spec, some appendix in the spec. So why do we care about this? Well, I guess, again, I'm kind of preaching to the choir with this audience, I would hope anyway. But let me reiterate anyway why we care about formalization. So one obvious advantage is it gives you higher precision about what's going on, right? With most of the mainstream language specifications, it's a combination of prose and wishful thinking, essentially. And when you do it in a formal way, there is no way to take shortcuts. You really have to spell out all the details. And that, of course, also is leading to, hopefully, a more correct specification, especially when you actually do proofs about it, right, like we do. So you have much higher assurance that what we are designing and defining here actually makes sense. And then there is the other thing for people, at least, who are versed in this kind of notation. It's also a much more efficient way to communicate, right? You saw in some of the rules, like for BR-if, there were like two-line simple rules, and the prose was like this. There are actually worse examples, so it's a much more effective and concise way of conveying what's going on with much less boilerplate. And then there's a last kind of advantage, which is often overlooked, that it also has an impact on the design itself. So when you design a language with formalization in mind from the beginning, then this creates a very important feedback loop. And it forces you as a designer to stay honest, right? You can't cheat anymore. So when you design a feature and you have to formalize it, it turns out the formalization gets really complicated, or you design a new feature and you see that it doesn't fit what you had so far quite well, then chances are there's something wrong with your design. I mean, not always, right? There can be cases where it's justified, but as a rule of thumb, if the formalization is difficult or complicated, then you might want to consider rethinking the design. And I would argue with WebAssembly, it has led to a simpler design or cleaner design in some cases. Okay, so this is all great. Oh, I should mention one more thing, of course. What we're doing here is we're standing on the shoulder of giants, right? So I cannot give a talk at an event like this, like ICFP, without mentioning these giants. And that's, in particular, this book, The Definition of Standard ML. This is from 1990. That was the first general purpose language that was fully formalized in its definition. So this is what it looked inside. It only had these rules. It was a work of elegance and beauty. It completely blew me away as an undergrad when I first encountered this, and I thought this is what everybody should be doing because it's so obviously better than everything else. Ours doesn't look quite as nice. We have all this nasty prose in between. Right, and they also didn't stop there. A few years later, they also managed to mechanize all that, so there has been follow-up work. So this was the first language that was fully formalized and also fully mechanized. And we're kind of taking that achievement and putting it into the mainstream, if you want. Okay, so this all sounds great, but there are some problems here. One is WebAssembly is large, right? So with WASM3 now we have hit the 500 instruction limit, or not limit, but like more than half. More than half of this is vector instructions, which is a whole zoo of like, yeah, annoying, irregular things. But even without that, you would have a problem, right? We also added a non-trivial type system. So the type system of WebAssembly used to be really trivial. You just had these 4 base types and that's it, right? Now with GC in particular and reference types more generally speaking, we have structural record types, function types. We have type recursion between them. We have co-contravariant subtyping and all these things, so it's no longer trivial. So this is the table of contents from the spec, and you can see it's around 240 pages at this point, plus another 80 pages of appendix, which contains, for example, these type soundness developments and stuff like that. So it's a lot of stuff. And it's not stopping there either, it's still growing fast, right? So there are still substantial features missing. We merged about 20 proposals since we started with WebAssembly, from fairly small to very large, but there are still as many still out there. Probably not, well, there's still a few big ones out there. So I guess the two important ones from my perspective, your mileage may vary, is that are not in there yet. One is threads, including the whole like relaxed memory model issue. And the other is what we call stack switching, so continuations essentially. From my perspective, those are the two biggies, but there are lots of others as well. So this is not like a solved problem. We have done all the work and now we can party or something. No, this is going to get back to us all the time. So, and to understand why that is a problem, well, how is the spec written? Well, actually the formalization that was written first, that was, for the original version, I wrote that it only took a few days actually to get the core of that right. And then it took a couple of, or more than a couple of months to actually write the entire prose, right? Because that is so much more tedious. So it's basically a handcrafted translation into stylized English. And as you can imagine, that's tedious and also very error prone. And it's also, the whole document is written in some markup tools called Sphinx, and it has all this embedded LaTeX, and you can't use any macros, so it's like really terrible. And all this kind of duplicate work of writing both these formulations, of course, has to be repeated with every proposal. And it's not just writing this stuff, we also have a process of code reviews, right? So our spec sources are on GitHub in the open, and when a proposal is written or being merged, then the editor, which usually is me, has to review all these changes, right? And because, like, I don't know, have you ever reviewed LaTeX code? That's basically write-only code, right? And some of the diffs are extremely large. So that was the biggest one, was the vector instructions when we added them first. That was more than 20,000 lines of code added to the spec sources, just the spec sources. Plus, I don't know, 80,000 lines of tests, actually. And that, again, is just speaking about the document and its sources. And then there's the mechanization, which is a whole yet different story. So again, somebody has to sit down and hand translate all these manually written paper formalism into something that a proof assistant would understand, something like Hawk. And as a result, they obviously are challenged to keep up, right? So there's obviously is a problem here. It's sort of an engineering problem, like how do we make this scale? And it's not like we're surprised by this. It was kind of obvious when we started that we would run into this eventually. But WebAssembly and the specification for it together.
Do we have stream audio now? Yes. Okay.
Okay. Oh yeah. Right. So I probably won't have time to go into the fourth part, which is the concrete syntax. That is also not overly interesting, but I want to go through the first three parts a little bit. So I said we have to start with abstract syntax, right? That is the core of anything you want to formulate. So in SpecTec, you can define abstract syntax by syntax definitions. So let's say, for example, oh yeah, sure, absolutely. Thanks for. There's quite some delay. Oh, that may be a bit too much, but okay. Okay, let's say for the types, so WebAssembly has this notion called value types, which are the types of primitive values. For this demonstration, let's keep it very simple. So say we just have two, which is I32 and I64, right? So that would be your abstract syntax for value types. That is quite boring, but you can see how to read that. I guess I don't have to explain that, right? It's the alternative of two things. Let's look at instructions. Let's take a tiny instruction set with a couple of instructions. Let's start with the most important one, the NOP. That's the instruction doing nothing. Then another simple one, let's say drop. That's the instruction that just drops some operand from the stack on the floor. Slightly more interesting would be something like select. Whoops. So that is kind of like a conditional, but an ego one. So it takes three operands, and the last one being an integer that decides which one of the other two to pick. We want actual values themselves, so we have to have some notion of constant. So in WebAssembly, we have the const instruction, which allows you to push a value. And that has two immediates now. One is the value type of the constant you want to push, and one is the constant itself. So these are now other pieces of syntax I have to define. I already defined value types, but now I have to define what a constant is. And for the purpose of this demonstration, I want to keep it really simply and say these are just natural numbers. So nat is a built-in type in SpecTec. And in SpecTec, you have to kind of write these sort of like data types. So they have to usually start with a constructor. That is not quite the syntax that WebAssembly itself is using. So we can give SpecTec some hints for how it should render this when it's printed, right? So we can say something like this. That would say that when you see a const constructor with the two arguments rendered like this, and that is the actual WebAssembly syntax that we usually use. Okay, this is slightly too large. Okay, maybe two more instructions to deal with locals. So we have local get, which takes a local index as an immediate, and local set similarly. So locals are just indexed by numbers, so we again have to define what a local index is, and that for now we just say again it's just a natural number. In reality it's bounded to 32 bits, but let's not be too pedantic about it here. So for this demonstration, let's say that's WebAssembly, okay? Very, very small and tiny, but good enough. So that's our abstract syntax for that. Maybe let me check whether that, okay, so SpecTec doesn't complain. I didn't make a mistake so far. So let's move on to validation. Can't type. Validation. It's not that hard, man. So we have to define typing rules. So, and these typing rules, they form a relation, right? Basically. So the feature that WebAssembly has, the SpecTec has here to do this kind of things is defining a relation. So I declare a relation, say I have to give it a name. So this is the relation that types instructions. So let's call it instruction OK. And I have to spell out the shape of this relation and the notation I want to use for it. And in the simplest case, it would be just assigning an instruction type, I go back to that in a minute, to an instruction. For various practical reasons, we want to be a bit more general and have the relation assign instruction types to instruction sequences. So instruction type is, again, just a piece of abstract syntax we have to define. And that is, we have a stack machine, so every instruction is characterized by what it pops from the stack and what it pushes from the stack. So it's essentially a function, or a combinator, really, if you're a functional programmer. So an instruction type is essentially going from a list of inputs to a list of outputs. So the list of things it pops to the list of things it pushes back to the stack. And I can write this cleany star here is the notation for lists. We can also use question marks or pluses here, which is sometimes convenient, but I think this is hopefully self-explanatory. And the arrow here is just notation that we introduced. That's just user-defined notation. So SpecTec has a bunch of these operators built in as a kind of atoms that don't have any semantics, but you can just use them to define syntax. So with this, we can already define some simple typing rules. So a rule now, for every rule, you have to say what relation it belongs to. And then you have to give it like an individual name. So let's start with the rule for knob. We just call it knob. And the knob instruction, now I just have to basically match the pattern of the relation I have defined. None of this should be surprising if you know how type systems work, right? Like, but this is how you write it down. And knob doesn't expect anything on the stack, neither does it push anything. So the sequence is empty. So epsilon is our notation for the empty sequence or the empty list. So that's the type of knob, right? That's the most trivial one. Drop, slightly more interesting. That takes a single argument and doesn't produce anything. And here I'm just writing t as a meta variable for this rule. And of course, SpecTec can figure out from the types I declared now that this has to be a variable that stands for a value type. And there's no constraint on t here, so you can instantiate that rule with any value type you want, and it would always apply to all of them. The next one, what did we have? Select. Slightly more interesting because that has 3 arguments, 3 operands from the stack. So 2 arbitrary values and another one that has to be an I32. That's the condition we're using. And it returns one of the 2 t's, right? And here we're using the same meta variable multiple times, which means they all have to be instantiated with the same type, as you would expect. Okay, next one would be const. Const also has a type here, and it has a constant. And conveniently, we can just read off the type, and it's t. So it's not much we have to do here. Now we're getting to locals. Okay, so local get. Well, what's the type of that? It doesn't take anything, so the left-hand side is epsilon. it returns some t, but that's not an arbitrary t, right? So it's the t of the local we have declared. I mean, this language doesn't actually include the declarations for locals, but let's ignore that for now. So assume every local has a given type. So this is where we need a context, right? So we have to be able to look that up. So that's why typing rules really are not just of this naive form we see here, but you usually type under a context, and you use this turnstile notation. This says that this instruction sequence has that type, assuming that typing context. And the typing context is again just a piece of syntax that we can define in SpecTec, and here it's convenient to use one features of the SpecTec meta notation, which are record types. So our context can be a record of different namespaces. For this simple example, we just have one, so it's a bit overkill to use a record, but just to show how that works anyway. And in WebAssembly, it's convenient that all our like locals and other namespaces too, they are always just indexed by natural numbers. So we can represent the typing environment just as a sequence of the types of these things. We don't even need a map for that, right? It's just that is the types associated with all the indices. So having that, we now need to adjust our rules here so they all actually take that context. So I was lazy before not doing that. I also have to instruct SpecTec that uppercase T, which would otherwise syntactically be parsed as a constructor kind of thing, is to be treated as a variable of a specific type. And now we can formulate this rule and give it a side condition. So you write side conditions sort of upside down from inference rules using a double dash, and then you can have a Boolean side condition writing if. And in this case, we will want to look up the type of X in C, so we can take the field of that record and index into it, and that gives us our T. So that's all there is to that. And local set is almost the same, except that the direction here switches around. Okay. And finally, you need rules for sequencing instructions. So this is individual instructions, but I said that the relation is supposed to type sequences of instructions. So how do I do that? Well, I can there are multiple ways to formulate it, but let's do the symmetric way. So if I have two sequences of instructions, and I can use these underscore numbers like in LaTeX to distinguish them. Then they have a type T1 star to some T2 star, provided, and now there's the recursive case or the inductive case, so we inductively apply the same relation, so we have to write it like this. The premise here is apply the same relation to either part, right? So if that has the type T1 star to some intermediate thing, T star, and similarly T2 star goes to, T star goes to T2 star. Then we can just plug them together, and that's, everything should be what you expect, right? Nothing fancy going on here. And then we also need to be able to type the empty sequence. That is sort of trivial. That's just this. Okay. There's one more rule you actually need to have, which is sort of weakening rule, but I will skip that. And rather, in the interest of time, go to execution. So as I mentioned briefly before, our execution is defined in terms of small step reduction rules. So rules that tell you how to take a single step on a sequence of instructions and go to a new state that has one step less work to do. And again, we can define that using a relation. So let's call that the step relation. And the step relation takes a sequence of, in the simplest form, a sequence of instructions and maps it to a new sequence of instructions, a simpler one. And the idea for execution is that you apply that over and over until the instruction you have arrived at is in some sort of normal form, and the normal form is being that all the instructions are values. So with expression languages, you usually do that. You have your constants as a subset of your expressions. Those are the values. And we can do something very similar for WebAssembly. So we can define the syntax of values as just the const instructions. And SpecTec will realize that this is a subset of the full instruction syntax we defined earlier here, which had this as just one case. So essentially, your program has terminated when you've reduced to a form where all the instructions here are just values. That's your resulting stack, essentially. There's one more thing. This is not actually enough because we also have locals, which are a form of state that we have to look up. So really what we are reducing is not just the instruction sequence, but we have a so-called configuration, which is a pair of some state and an instruction sequence. And again, the semicolon here is just notation I picked, has no semantics. And then the sequence, the relation really is over configurations. Sorry, keep mistyping that. So there's state here, so we have to define what that is as well. And in our simple case, we can again use a record here. We only have locals, so the state of locals is, well, they're values, so this is just a sequence of values, essentially. That's our state, our local state. Okay, and now we kind of proceed in a similar fashion. Basically, for every instruction, we want to write one rule. So let's start with knob, which is sort of easy. So we have the state and the knob instruction, and that reduces to the same state because it doesn't have any side effect, and the empty instruction sequence, which means there's nothing left to be done to execute a knob. Right? For drop, we start similar. Yeah. So that also reduces to something empty, but it takes something from the stack, right? So which we can express as being there isn't a constant instruction before that. And that is what we have defined to be a value. So if you have a sequence of an instruction that is a value and a drop, then they can react and turn into the empty sequence, right? That's how you reduce. And when you do that iteratively, then you reduce your program. So I don't know if you can see that if it's so low down. Select now is actually doing a little bit more work. So with select, we have two values and a third value, which is required to be an I32 constant. So we can kind of pattern match it directly here with some value, and you have a select after that. So what does that reduce to? Well, in one case, it reduces to val1, which is exactly the case if C is not 0. Okay, but we need a second rule for the other case. So there are now two rules here. So this would be true. Let's call this false. And then in this case, we reduce to, oh, sorry. Of course, this should be val2 here. And that's all you ever wanted to know about conditionals, right? You don't have to write a whole bunch of stuff. It's just these two rules that describe how a conditional works. And finally, we have locals. Local get, and this is where the stack comes. The state comes in. Oh, actually, I have to put the state here as well. Otherwise, it will complain. So we have local get x, and that goes to the same state and some value. Where does that come from? Well, we have to look it up. So if s locals x equals val, right? And the last one is set. this doesn't return anything. Instead, it expects something. So it's a val here. And it also changes the state now. So we get an S prime. So our site condition now is, what is S prime? And S prime is an update of S, and there's some notation, meta-level notation that SpecTec understands, which is, okay, I want to be that the same as S, except that .locals.x has been replaced with val, so that you can use this kind of path and replace that. So that's our entire reduction rules for this language, minus you need some contextual rules about like how you find the regex in a sequence, but again, I'm going to skip that here in the interest of time. And I effed up somewhere, 37. Oh, yeah, that should be this. Okay. So this is our specification. Well, we're not done there yet. We want to generate a document that nicely prints it, right? So that I prepared a little bit. So here's kind of like a template for this document we want to generate. So this is written for the Sphinx document processor. So you write a bunch of text here, and the interesting thing here is that for SpecTec we can put in these clauses, these splice clauses. And then we can run SpecTec over it. It will interpret these and insert the definitions to do so. So for that, I built a little make file so that I don't have to remember the exact invocation. Oh, okay, I renamed something. Sorry. I did it a bit differently before, obviously. Can never remember what I did last time. Right, so this succeeded now. And it produced an RST file with all the things spliced in. So this is now all the LaTeX it generated from this ASCII formulas. So it's nasty stuff you really don't want to write manually. It also generated prose for us, which is a bit harder to spot here. So let's actually generate a PDF from that to look at that. And nanoWASM PDF. Right, so this is now the document. Well, I had some template that does the whole thing around it, right? And there is a table of contents, blah, blah. So you have the abstract syntax, which is defined here. So this was text that was literally in the template that was not generated. But if we go to, for example, all this text here is generated, right? So I just wrote the rule and the text is generated now. Maybe a more interesting case is the one for execution of select, for example, right? So now there are the two rules that you might recognize, but all this text now is generated automatically, and it knows that it has to somehow merge the rules and turn that into a conditional to produce this text. All of that is now nicely generated. How much is it left?
0 minutes.
0 minutes. Okay, I'm just going to show the final slide here. This is how it looks on the real document. I'm going to skip that and just have the summary slide is why this is so useful, or what are what we get out of that is more efficient design and authoring, so that benefits proposal writers and spec editors. Higher assurance, as I mentioned before. And we also hope, as a third thing, like in the future, that other kind of tools can make use of having this machine readable form of specification. And there are already some in the making, like Dongjun, for example, is working on a test generator, right? So this would be a smarter fuzzer that doesn't just randomly fuzz WebAssembly code, but actually understands its semantics, right? So it can take that into account. And you can imagine various other code tools that, or like verification tools that can now read in this definition and do something smart with it. Okay, I'm going to stop here. Thank you.
Thanks so much. So, let's take a short moment for questions. The way we'll do this is, Andreas, can you come to the side? Anyone who wants to ask questions, come up to the mic. Can we get our next speaker coming to set up their laptop? as we do this.
Yeah. Take that. Oh.
So you talked about a whole bunch of things that you generate, but you didn't talk about what I think is the most important part of the specification, which is the reference interpreter.
Well, I briefly talked about one version of it.
Uh-huh.
Actually, it's not really a generated interpreter, but it's a meta interpreter that runs on the specification you give it, right?
And does this sort of completely replace the reference interpreter now?
No, it does not. And that is something that is maybe some future prospect, but there are lots of things we have to work out before being able to do that. Right now, that can only interpret the execution rules. It can't do parsing, it can't do validation and all these things, right? I also didn't really talk about much about the whole mechanization side of things, but yeah, that's basically the second phase of our project. That is the ongoing work happening right now.
Yes, watch this space.
Exactly, yeah. Any other questions?
One more question. How do you think we're going to fund continued development?
Don't ask me. That's your job. No. Yeah, I think that's still the biggest question. Like, how do we sustain this kind of project long term, right? Because especially the mechanization, but actually all of this is mostly done by academics, or yeah, and the nature of academics is that they tend to like to move on and they want to do publications, and like extended maintenance of software projects is not something they really get anything out of. So how do we do that? It's a bit of an unsolved problem. Right now we have a huge team and a lot of funding, relatively speaking, but is this going to stay that way? So that's definitely something we have to figure out still.
Okay, thanks. I'll speak on that side.